Okay, so what we'll be looking at basically is how we can model the PVT data. We have been seeing some of these concepts, but we want to look at how we could move beyond the basic concepts that we have been seeing, like PVT matching and all of that. So the first thing is, what do we consider as a model? Because there are basically two forms of equations that we can use to carry out modeling in real life. So what we have here is a simple definition of what a model looks like. A model is when we have a phenomenon that can be measured by numbers. Then we relate the phenomenon parameters by an equation or correlation. That's what we mean by modeling in terms of PVT data. Now, because generally when we talk of a model is just a picture of the reality. What looks exactly, how we can produce something that looks exactly like the reality. Is just like a photocopy. You have an original copy and you want to produce another copy that can behave or looks exactly like the original copy. So when we talk of modeling a reservoir, for example, we want to produce a picture of the reservoir. We want to produce a 3D model of the reservoir that looks exactly like what we have in the subsurface, so that we can try to simulate the behavior during production or the behavior of fluid flow within this reservoir. So there are two types of mathematical relations that we have when we want to model a PVT data. We may have an equation that have been derived from a physical experiment. For example, we all know this law, PV is equal to nRT. You must have seen this from chemistry classes from secondary school. You must have seen all of this. We have the real gas equation, and then we have the ideal gas equation. So this is the ideal. So this equation was formulated from a physical experiment. Some kind of apparatus was set up, an experiment was conducted, and this formula was derived. But when we talk of a correlation, it is not the same thing. A correlation now may just be to look at two parameters and try to bring out a relationship that can define these two parameters, how they are related. For example, I may have a plot. This is our X. This is our Y. I have plots there, points there that have been plotted. So you may want to do some kind of regression analysis to find a relationship between X and Y, probably by looking for the best fit line. You can draw the best fit line that best define this point. When you draw this best fit line, you can calculate the equation of this line. You calculate the equation of this line, we may say y is equal to, for example, it can give us 2x minus 3. 2x minus 3. So that gives us the equation of this line. This was not derived from a physical experiment, but from analyzing the relationship between two parameters. So this is called a correlation. So that is the main difference between an equation and a correlation. Because what we saw in Prosper and even in BAL when we're doing PVT matching was to use some correlations that have been derived by others. they did not derive these correlations or they did not derive these expressions by using physical experiment, but by studying data and trying to look at the relationship that coexists between them, and then trying to see how we can bring out some relationship that exists between them. You must have seen some of these concepts in statistics, in basic statistics. All right, so that's basically the main difference between equation and expression. All right, so this is just an example of a correlation. How you can use other properties to predict other properties. In this case, this is a correlation to calculate the bubble point pressure. We have the gas gravity, we have the solution gas, we have a solution gas, and also depends on a parameter A. This parameter A will depend on pressure and the temperature condition. So this is an example of a correlation. This is an example of a correlation. And you can use, there are so many correlations that exist to calculate the formation volume factor, viscosity, oil, gravity, and all of that, which we have already seen some of them. So why do we have to model our PVT data? Why do we have to model our PVT data? You realize that generally what the company does is when they collect fluid sample from the reservoir, they have to take this fluid sample to the laboratory and then subject this fluid sample to different pressure and temperature conditions. Then they now analyze and determine these various properties at different pressure conditions, probably by changing the pressure value. Then they measure all of these parameters. They might measure it up to a certain pressure, let's say 2000, 2500 psi. But in a real situation, in a reservoir condition, you may have different pressure regimes, pressure values that are beyond those values that were measured in the lab. So what they have to do now is to find a correlation that best matches with this PVT data, so that when they get to a point where they have to know this particular property and it was not measured in the lab, this correlation can be used to predict that particular property. So there are so many reasons why we are doing PVT modeling. So in this case, the first point is a blind case. Said, as in many cases, we don't have a PVT sample to get experimental data. So we use the well-test available data like API or gas gravity. So you don't have all the properties, or there is no means for you to determine all the properties, but you have determined a few of them: gas gravity and the oil gravity and the oil density. So you can use this now to determine the reservoir property. So that's why they are talking of a blind case, a case where you have no experimental data. And then the next case now is extrapolating. That's exactly what I'm just from explaining. Extrapolating beyond regions where you could not measure them in the laboratory. So this is the basic reason why we have to carry out PVT modeling. So the next aspect is PVT modeling methods and criteria for selection. So what are the various modeling methods that exist, and why do you have to choose a particular modeling method? We are talking of black oil model. We have compositional model. Why do I have to choose black oil, or do I just get to any well and I just decide to choose black oil, or there's a particular criteria that you have to follow in order to choose either black oil? We have also what we call modified black oil, and then, or we have the compositional model. But generally, we'll just merge it into two, black oil and the compositional model. Why do we have to choose any of them? So this is what we want to discuss. And the first aspect is we'll just pick one on one and then we discuss on them. So if you look at the black oil model, you realize that the first thing is to understand how you classify reservoir fluid based on the change in temperature. Based on the change in temperature. If you look at the phase envelope, when we have our PT curve, when you have the phase envelope, you realize that we have the two phase region. Don't know if I have a plot for that. Anyway, let me just. So we have this is our PT curve. This is our PT curve. We have our two-phase envelope. That's our two-phase envelope there. That's our critical point there. That's our critical point here. Above here, we have oil only. Here we have two-phase, oil and gas. And then here we have gas. So the predominant property that controls the behavior of gas is temperature. And the predominant property that controls the behavior of oil is pressure. We are not saying that the other one will not contribute, but we are talking of predominantly. So if I have a fluid that exists at this point, is a black oil. That's a black oil fluid. As you're moving away with increase in temperature, we now have the volatile. We move from the volatile to the gas, to the condensate. From the condensate, we go to the wet gas. And from the wet gas, we go to the dry gas with increase in temperature. So we have basically about 5 different types of reservoir fluids. We have black oil, volatile, we have condensate, we have wet gas, and then we have the dry gas. All right. So we are saying that for a black oil, it is generally used in a situation where you don't have wide variation of PVT parameters. These parameters do not change very widely with pressure and temperature. In this particular case, we use the black oil model. And this case will be true for two types of reservoir fluid, for black oil and for dry gas. This particular case is suitable for these two types of fluid. That means if I have a dry gas, I can also use the black oil model. If I have a black oil, I can also use a black oil model. So these particular cases black oil model can be used to model these particular cases because their properties do not change widely with changes in pressure and temperature conditions. Okay, so we have talked of black oil is just a name, but it's used also in modeling dry gas properties. So they have given an example of an equation that we have already seen. All right. So the next model now is a compositional model. In the compositional model, the properties change widely with the change in pressure and the temperature conditions. So every aspect about the condition of the hydrocarbon has to be defined in terms of the pressure and the temperature, because these parameters will go a long way in defining what that condition would be. If you don't define these parameters, you cannot fully understand how the system will behave. But in a black oil model, we don't need to relate or to understand these parameters that much, because no matter how the pressure and temperature condition will change, these properties within the fluid will not really change that much, So in this particular case, we have to bring out an equation that clearly defines the state of the fluid, and this equation is what we call an equation of state. So equation of state is used for a compositional model. And for this compositional model, you must be able to know the exact components that are found within the hydrocarbon and their various mole fraction or mole percentage. If you don't understand this, you won't be able to develop an accurate equation of state. So this is the main difference between compositional and the black oil. Because for black oil, I don't need to understand the chemical composition. I don't need to know the chemical composition of the fluid. I just need to know some 1 or 2 parameters and I can model the behavior. But for a compositional model, you need to know the exact composition of the hydrocarbon. From there now, you'll be able to develop an accurate equation of state that will be able to be used to predict these properties at different reservoir conditions. All right. So now we are talking of reservoir fluid typing. Typing used in reservoir engineering is just a term to describe maybe changes at different conditions. We have a reservoir pressure that varies between 2,000 and 5,000 psi, and then we say between 2,000 and 3,000 we have a fluid that behaves in a particular similar manner. Between 3,000 and 4,000 we have a different type of fluid that behave in a similar manner. That means as the pressure is changing, the fluid is now transforming. The fluid is now being transformed because of that change in the pressure and temperature condition. So that is described as fluid typing. We also have what we call rock typing also, where we have the ability of a reservoir to be divided into discrete units that have different flow characteristics. So in this case, we say generally we use black oil modeling in case of reservoir fluid without high compositional variation during depletion, or reservoir production timeline, like a case of heavy oil and ordinary black oil and dry gas reservoir. So you don't have that variation, that huge variation. It may be slight. We are not saying that it will not change at all, but the variation may be very, very slight. Compositional modeling, we have near critical oil and gas condensates. All right. So what are the various fluid types that we may have after laboratory experiment, and how can we use them to be able to produce a PVT model of the various fluid? If I collect a fluid from the reservoir and I sample it in the laboratory, if at the end of the day it proves that we have a black oil reservoir, which we have already explained, this black oil reservoir could be a black oil or it could be a dry gas. In this particular case, there are 3 ways in which you can model the fluid. You can just simply use the laboratory data. If the laboratory data is within the range of our reservoir pressure and temperature condition, we can use a correlation, not laboratory data. We can choose a correlation that best matches the actual laboratory data. That's what we were doing in Prosper when we were talking of PVT matching. So you have to either you use the table, the value that you obtain from the lab, or you choose a correlation, and we have to do what we call PVT matching, choosing the best correlation that best matching our data. Or you can still develop an equation of state, even though this third part is not widely used for a black oil model. It's mostly used for compositional model, but it is still possible for you to develop an equation of state. For a modified black oil reservoir, I think it's just similar to the black oil. It's just a modified or an upgrade of the black oil. I said we'll not dwell on that. We'll dwell on black oil and compositional. So if you analyze your fluid and it ends up that the fluid is either a volatile oil, or a gas condensate, or a wet gas, or a wet gas, not dry gas, because we have seen that for dry gas, we can use the black oil model. In this particular case, we have just one way of modeling that fluid. There's no two way about it. You cannot be talking of PVT matching. There is no matching in this case. In this particular case, we must develop an accurate equation of state that can be used to predict the reservoir properties. That can be used to predict these reservoir properties. All right, so we move beyond that. So this is just to tell us that for a compositional model, there is no way you can use correlation. That's why you're seeing an X on that. There is no way we can use a correlation. Now, before you model, there are some 1 or 2 parameters or data preparation that you have to put in place before you start the modeling. For a black oil model, all available experiment data like the gas oil ratio, the oil density in API, and then we said, remember, we just select the correlation that best match our data. All right. Any predicted data does not depend on matching. So our predicted data, any data that you're predicting, you're using the correlation to do that prediction. But for compositional models, we adjust the component properties, especially we are going to see all of this when we look at the analysis using our PVTP software, But you need all the composition of the hydrocarbon before you can be able to carry out a compositional model. Now, what are these equations of states that we are talking about? What are these equations of states? 1 or 2 of them should be equations that you are very familiar with them. You must be familiar with some of these equations because you have seen them in chemistry. All right. And so an equation of state, say, is an equation that simulates each component behavior in the composition under various operating conditions. So they have just given what we have been talking about. Why need equation of states? Why do we need equation of state? To check if PVT analysis are reasonable or not. To carry out quality checks on PVT tests. So we should be able to QC our PVT tests after the laboratory analysis to be sure that everything was done properly well in the lab. So generate PVT data for the range outside the laboratory measurement. So you can also use the equation of state to predict PVT data outside the range. Maybe you have worked between 500 to 2000 psi. You can now predict the behavior between 2000 to 5000 psi and all of that. All right, so what we have here is just the history of equation of states. That one is not too necessary. All right, So we have basically three types of equations that can be used to model fluid behavior within the reservoir. We have the ideal gas law, which is definitely a combination of, I think it's Boyle's law, Charles' law, and pressure law. We saw all of this. I think we must have seen this in basic chemistry and physics. We have the ideal gas law. We have the real gas law, because generally within the reservoir, the fluid will not behave like an ideal gas. Gas behave ideally at standard condition or very close to standard condition. Standard condition of 60°F and 14 point something psi pressure. So that's your standard condition. So at that standard condition, our gas is going to behave in the ideal manner. Beyond that, it can no longer behave in an ideal manner. So it behaves like a real gas. So we have to measure the deviation of this gas from the ideal situation. That is going to bring in another concept which we call the gas compressibility factor. The gas compressibility factor, which you must have heard in class. All right, so the third part now is an advanced method now of developing our equation of state, which we call the cubic equation of state. And the most widely used among this method is the Penn-Robinson equation of state. All right, so we look at the ideal gas. The ideal gas law is just simply gives us PV equal RT. So definitely, as I said, we must have seen all of this in basic physics and chemistry. Now, for our real gas, we now have to bring in an aspect which is called the compressibility factor, which is Z. The gas compressibility factor is a whole lot of work to be able to analyze and determine the gas compressibility factor. I'm not sure we have seen any example on that, but there's still no issue. Maybe we'll look at it tomorrow. So this Z factor now, which is called compressibility factor, is a measure of how the gas deviates from the ideal situation. How does it deviate from the ideal situation? If we have a value of about 0.9 something, it means that it is close to the ideal situation. Because remember, if Z is equal to 1, then this equation becomes the ideal situation. So the further this value is away from 1, the further that fluid is deviating from the ideal situation. So if I have a value of 0.9, it means it is closer to the ideal situation. But if I have a value of 0.6, for example, it means that the fluid is behaving very far away from the ideal behavior of that particular fluid. Okay. So we'll move away from that. I said compressibility factor is another ball game. We are just introducing here. We must have seen all of that in class. And this compressibility factor depends on pressure, depends on the composition, depends on volume and pressure and all of that. And to characterize this compressibility factor, we have to bring in the aspect of pseudo parameters. We have to bring in the aspect of pseudo parameters into play. Now, the first model under the cubic equation of state is the Van der Waals model, and he developed this in 1873. And this is the exact equation. We have P is equal to RT all over V minus B minus A all over V minus B. So you realize that in this case, the volume is now playing an important role in that equation. The volume is playing a great role in that equation. And that is the reason why we don't even need equation of state for black oil modeling. Why? Because the volume does not really change. The volume of the various components or the various aspects about the fluid does not really change that much with PT condition. Remember, when we are talking of compressing gas, you can take air, for example, that can fill a whole room, and you compress it to fill a very small container. But there is absolutely no way you can do that when it comes to oil. So you realize that in this particular equation, there are two aspects that is coming in, two parameters, which is A and B, that has to be determined also. That means if you have a particular data and you want to use the van der Waals equation of state to model that fluid, your main concern first, it will be to determine the value of A and B that will clearly define this equation. All right. So during this experiment, van der Waals realized that when you plot a graph of pressure and volume for a particular fluid, all of them will follow this particular pattern. And you realize that from your basic concept of mathematics, this is a turning point. This particular point over here, which is called the maximum point, is a turning point. And at this point, which is called the turning point, the gradient of this particular graph is 0. The gradient of this particular graph is 0. And generally, the gradient of a graph is obtained by differentiating that particular function. So if I have this function, if I want to know how the gradient or how the curve is going to slope, what I will do is to differentiate this function with respect to volume. So once you differentiate that function with respect to volume, it will give us the gradient at each point within that particular curve. And at this maximum point, that derivative is equal to 0. And this maximum point is always obtained at the critical point, at critical condition. It is always observed at critical condition. So at critical condition, we know that dP on dV will be equal to 0. And definitely if dP on dV is 0, then the second derivative, d squared p on dv squared, will definitely be equal to 0. So the easiest way for us to calculate the value of A and B is to differentiate this function, equate it to 0, take the second derivative also and equate it to 0. And remember that it's becoming 0 at a particular PT condition. And this PT condition is generally at our critical point. So from there now, we can solve these two equations in order to calculate the value of A and B. All right, so that's for the van der Waals. And then they have now simplified it to tell us that this is the value of A and B. This is the value of A and B. All right, so we move to the next. This is still van der Waals. All right, so now the equation also can be simplified by bringing in this relationship. PV is equal to ZRT. Because if you look at the equation keenly, you realize that it depends on P, R, and V, which are the parameters that are changing. Remember, R is a constant. I think it's called the gas constant or something like that. So what this equation depends on as variables are P, T, and V. But we may also want to develop an equation that will incorporate the Z factor also. That will bring in the Z factor. So if we take in this Z factor and input into this equation, we can now simplify it to have an equation that looks like this. Remember this equation, we have R there, but all right, that's, yeah, R is our universal gas constant. That's okay. All right, so if we bring in the PV is equal to ZRT into this equation, you can now eliminate R and T. And then from that equation, you can bring out this parameter that depends solely on Z. So we have eliminated PV and T, including R, and then we have an equation that depends solely on Z. And in this case now, we have a new parameter, capital A and B, that are defined in this manner. Our A is now depending on small a, and our B is now depending on small b. So there are other correlations also that can be used to also get the value of A and B. That's what we have here as A and B. In this case, we have ohm. This symbol, what is it called again? This symbol for resistance. The name just escaped my memory. Yeah, I think it is ohm. Yes, that symbol is for ohm. Yeah, the SI unit of resistance. All right, so from there, it depends on ohm A and ohm B, and these values have been given. And then from there, we have our gas constant. That's a particular value of 10.73. Is based on this particular SI unit. You may have different values at different units. This one is in field units, where we have PSI, we have feet, and then we have temperature in Rankine. Temperature is in Rankine here, and then we have our critical pressure and temperature. So you can also use this correlation to obtain the value of A and B, like what we have here. Okay, so in this particular equation of state, we can have the value of A and B. That means if you can use your data to be able to obtain the value of A and B, when you substitute it inside this equation, you can now use that equation to be able to predict what the compressibility factor will be at any given pressure and temperature condition. So they said the Van der Waals gives a qualitative good estimation of hydrocarbon properties. All right. So our next equation now is the Redlich-Equan equation that was developed in 1948. So in the equation, you can actually see a difference from the Van der Waals equation. And we still have our parameter A and B. The only difference is that there is some kind of a modification at this level. And it brings in a new term that has to deal with the attractive forces that exist between the molecules. So there is no big difference in the manner of estimating the value of A and B. It will follow the same procedure. So if you take this, we can also transform it into this Z. Then we have our A, B. We still have our capital A and B in this case. We have our capital A and B in this case. Remember, this small a and b is obtained by solving this equation when the derivative and the second derivative are equated to 0. So that is our second equation. Our third equation of state, we still have in a similar manner, just changing, but we still have our parameters A and B coming in, and another parameter alpha now comes in this particular case. So this particular equation is just a modification. It's just a modification of the Redlich-Kwong equation. That's why in most cases, you will not just see swaths you will just see as SRK because this guy came in and modified Relish Quam equation. So it's just a modification. So another parameter alpha is coming in. So that alpha now can be defined at every temperature condition. So the alpha depends on the temperature condition, and the alpha depends on M, and M also depends on another parameter which is called omega, and the omega is the eccentric factor of the substance. So each substance has its eccentric factor. All right. So this is basically what we have on the equation of state. So I will just send the PowerPoint. You can use it. This is the eccentric factor that I've discussed more about. But my idea here was just for you to understand what are the various models for PVT modeling, and why do we have to choose some particular models in which case, and what are the various formulas that we have. All right, so we'll end there today so that you can digest on the theory. I will send this. It's a very long, PowerPoint. I've just concentrated on that part. I've just concentrated on the part of PVT modeling. So if you want to learn better, you can go through the PowerPoint. I'll give this PowerPoint to you. You can go through the PowerPoint. I've concentrated only on the aspect of PVT modeling. All right, so if there's any question, you can ask. If there's no question, we'll meet tomorrow to do the software analysis. All right, so it seems there's no question. We'll meet tomorrow.